All right. Jumping back into the lectures though, let's jump into section 1.4. 1.4 is all about functions. What a function is it takes a value for what's called your domain and sends it to a value in what's called your range. So it's really just a relationship between two sets of numbers. In some ways, we can think of it as a machine, right? You're taking inputs from your domain and you're sending them to outputs in your range. That said, a very, very particular important rule to what it means to be a function, a particularly important rule, is that you can only have one output for every input. So when talking about these, this is the equation of a circle, right? X squared plus y squared is equal to 1. So we have in B, a circle with radius equal to 1. This is just B. If we put in one x value, we get out two y values. So let's put in 1/2, negative 1/2. Negative 1/2 is equal to x. Well, we get out two different y values. So B can't be a function. But C, well, C could be, couldn't it? C, let's rewrite C as y is equal to 1 minus x squared. Well, this thing's going to look like this. Caught it. And they say mathematicians can't be athletically inclined.
Did you play any sports?
Wow, okay.
Did you?
Let's get personal now. Shots fired. Snowboarding, that's all I got.
It's more than me.
It's actually the only time I've ever broken bones with snowboarding. But I can't snowboard. That really did not help my defense at all, did it?
No, that made it worse.
Yeah, kind of, yeah. So, looking at this example C, we've got a parabola facing downwards. It's got two different x-intercepts, one y-intercept. Is this thing a function? Yeah, right, because every x value only has the one y value. So the difference between being a function and not being a function is just that every one of your x values have to have one y value associated with it. So everything you put into your function spits out one answer. Now, one way to evaluate B is to actually solve that equation out. When we do that, we get that y is equal to plus or minus the square root of 1 minus x squared, right? But notice what that tells us then is after we do this algebra right here, let's say we put in 1/2. Then we're gonna take the square root of 3/4. But we're gonna get two different answers. Because the square root of 3/4 is the square root of 3/2. But we have to tack on this plus or minus. So we get either a positive answer or a negative. So one x value is gonna give out two different possible answers. Does that make sense what I mean?
I have a question. It could just be that I'm sitting around trying, but both B and D are a no, and they're y squared. So does that mean if you see a y squared, it's not necessarily gonna be a
That's what I
function?
was thinking, yeah. Because there's only one y value, so.
So it's
Yes
squared.
and no.
It's not.
Yes and no is the best I can answer that right now.
Okay.
Because part of what we could do, later on, we'll see this, is say, we're only going to take half of these answers. We're gonna restrict the range, restrict the domain in some way to force the thing to act like a function.
Okay.
Does that make sense? So there is some truth to that, yes. Y squares will traditionally lead to this sort of a hiccup.
Okay,
Um,
but later we'll restrict it, so we can only get the functions that we want.
Right. We could later say, only take the positive y's. Okay, that's a function. And in fact, that's what we do oftentimes and not even realize it. But before we get there, just wanted to look at some of these functions really quick, what they actually look like as graphs. So I drew B and C on the board, but notice B and D both are the two that failed, right? And notice if we took a straight line, straight vertical line, and moved it all the way through, for pretty much all of that graph, we have to cross through 2 points at a time, right? So except at one, at -1 and 1, moving through, we're always going to cross through two sets of points, right? Similarly over here, up until 1, always going to cross through 2 points. This is what's called the vertical line test. It's a way of looking at a graph and determining right away whether or not that graph represents a function. Really quick, do I have anything about that? No, I don't. Okay. So another way of thinking of what a function does. All right. Let's say we have all these possible numbers. A group of them that we call X and a group of them that we call Y. Out of that group called X, only a handful of them might be applied to the function, right? Like the function might only work for some of them. One example we can consider would be something like 1 over X. You can put whatever number you want in there except for 0. So X here would be like all numbers. Domain here would be every number except for 0. Does that make sense what I mean? So what a function is doing then is it's taking an X value and sending it to a Y value. But only to 1. And like I said, we could have the case of all real numbers. So the funny R means real. It's just all real numbers. We could have something like this, where g of x is equal to 1 over, let's say, x squared this time. Then this, the domain, would be equal to negative infinity up to 0, unioned with 0 up to infinity. So what does this mean? This means you're taking every number from negative infinity to 0, but not 0. And then every number from 0 to infinity, but not 0, and putting those two groups of numbers together. This is the same idea as saying R minus just that number 0. Does that make sense what I mean? So we'll get more into some of this notation after a while. But for now, I just want you all to understand this concept of a function is just taking one x value, sending it into one y value. A domain is of all the possible x values you could potentially be choosing from, which ones will our function give us an answer to? So here, we don't get anything out if we put 0 in, right? So 0 is not in the domain. And then the range is all of the numbers your function will spit out. So having said that, the square root of x minus 1 well, the square root, we can put any number that's 0 or larger, right? So that means x minus 1 has to be larger than or equal to 0, right? Everybody agree with me on this? So that means then, adding 1 to both sides, x has to be greater than or equal to 1. Just solving inequalities here. And the way we got to this was, we said, what's the domain of that? I don't know. But the domain of this is any number greater than or equal to 0, right? So if that's the case, x minus 1, we can think of that as z. That has to be greater than or equal to 0. Because that has to be greater than or equal to 0, then x has to be greater than or equal to 1. Everybody cool with this? So here, the domain then is going to be x greater than or equal to 1. But what about the range? What possible values can we get out of this? Can the square root ever give us a negative number? No, right? That's the whole point of imaginary numbers. So our range is going to have to be anything 0 or bigger, right? That's going to be true no matter what you put through it, up to a point. So the range is going to be y values greater than or equal to 0. Does this make sense? Everybody cool with this? Yep. So just to reiterate, what they're saying here is x minus 1, it doesn't give you an answer whenever x minus 1 is less than 0, right? The square root of a negative number isn't in our answer set. Does that make sense? So because of that, the domain has to restrict x minus 1 to values greater than 0. Notice they're answering this the opposite way of what we did. They're saying things less than 0 aren't defined. We were saying things greater than or equal to 0 are defined. They're just flipping what we're saying, right? Does that make sense what I mean? So given that, our domain is going to be x greater than or equal to 1, which we can write in interval notation. So what is interval notation? Interval notation, you got a few different symbols. You got the square bracket, you got the square bracket, you got the rounded bracket, you got the rounded bracket. What these are doing is these are saying, starting, it'll be easier if I actually write out all the different combinations. You got something that looks like this, something that looks like that, something that looks like that, and something that looks like this. All right, what does this notation mean? This is telling you if you have, let's say, A to B. This is a set of all numbers from A to B, including A and B. But, however, if we were to round these, so let's say this, now we're saying every number between A and B, but you can't include A. So another way to think of this is to think of it in terms of our inequalities. This is the same thing as saying you have an x value that has to be bigger than A. It can be up to and equal to B, but it can't ever be A. Does that make sense what I mean?
Yeah.
So these rounded brackets correspond with greater than, less than, right? Less than, greater than, let me say. And the square brackets correspond to less than equal, greater than equal. Make sense? So square brackets mean you can attain that final value, A, or in this case, B. Rounded brackets mean you can't attain that value. You can get as close as you want to it. Having said that, as a point of notation, when it comes to infinity, you can never attain infinity. So if you end something with infinity, it always has to have that rounded bracket. If you begin something with negative infinity, you have to begin it with that rounded bracket. Because you can never attain infinity. Make sense? So another point about all of this function here is what's called a piecewise defined function, or piecewise function. What we're saying is whenever x is less than 1, our function acts like this. Is there a second floor to this?
There is now.
I didn't know that. Anyhow, whenever x is greater than or equal to 1, we take the square root of x minus 1. So what does that second function look like? Looks like this. The first set of rules told us what to do when x was less than 1. That was that line with negative slope of 1. The second set of instructions told us what to do from 1 and beyond. Make sense? So this is what a piecewise function does. It breaks up your function and says, whenever you have an x value that fits a certain set of rules, do this thing. Whenever you have an x value that does this other set of rules, do this other thing. Now, to that end, when talking about range and domain, something to notice. It'll be easier if I actually draw it up here. So this is that function, x minus 1, right? Square root of x minus 1. The domain could be thought of as the shadow cast by our function if we took a light and shined it perpendicular to the x-axis, right? Does that make sense what I mean? So if I were to take a flashlight from above and shine down, the domain would be all the x values hidden by the shadow of our function. However, the range would be doing the opposite, where you shine it onto the y-axis. Is everybody cool with that? So what that means is, if there was, for whatever reason, a discontinuity, we would say we would have a domain in this case that looks something like this. So this U is saying you add this group of numbers, that group of numbers. You're not actually adding the values, you're adding the collections of them together, they're pouring them into the same bucket. Similarly, we would have the same sort of thing happen in the range. Is everybody cool with that? Cool. We're going to see more of this in a second, if I remember my notes. So, just really quick, I wanted to, more than anything else, point out the notation here. Here we've got this idea of f of x. F of x is just our shorthand for our function. Instead of saying 2x squared minus 4x plus 1 every damn time, because that gets exhausting after a little while, let's just write f of x. And whenever we want to put a particular x value through it, let's just say f of whatever that particular x value is. This way we don't have to rewrite that equation every time. It's shorthand. That's all we're doing here. That's what this f is. It is essentially naming your function in enough of a way that you can say, what do you want to do with this function? What are you about to put through this function? Everybody cool with that? Cool. So, if that's the case, let's evaluate B really quick. I would like y'all to take 3 minutes to try and do B on your own. Then I'm going to do it up here on the board. Okay. So this is kind of unfair because I didn't quite tell y'all how to evaluate a function. I just said, this is a function, now do a thing with the function. What a function is telling us is, given some random x value, here we don't necessarily care what our x value is, we're just gonna call our value x. Given our value, you want to square it, then you want to subtract 4 times it from that square, and then you want to add 7 to it. So when we pass x plus delta x through, everywhere we see x here, we want to put x plus delta x into it. So let's say this was 4 plus delta x. Then you would put 4 plus delta x here, and 4 plus delta x here. Does that make sense what I mean? So now, with that in mind, A, what we're gonna do is we're gonna replace each of these x's with x plus delta x. That's what I've done up here. We're given the set of rules for what to do with whatever value. Now we're saying, all right, with x plus delta x as our value, how does this evaluate out? I went ahead and expanded everything. Since we're squaring this, we're gonna get x squared plus 2x delta x plus delta x squared. Here we're multiplying by -4, so I just went ahead and distributed the negative and replaced it with an addition up front, right? So we're distributing -4 inside, and nothing happens to our 7. And then finally, rearranging everything. So, with that, now we know what f of x plus delta, f of x plus delta x is. Now, we're going to answer B. What is f of x plus delta x minus f of x over delta x? I promise the answer is not torture, in spite of the fact that it may feel like torture. But we already know what this f of x plus delta x is because I just evaluated up here for us, right? So let's write that up. Is equal to the quantity x squared minus 4x plus 2x delta x minus 4 delta x plus delta x, that quantity squared, plus 7. Now we're going to subtract from it x squared minus 4x plus 7. And then we are going to divide by delta x. First things first, let's distribute that negative sign through. When we do that, and dropping the parentheses, we have x squared minus 4x plus 2x delta x plus, minus 4 delta x plus delta x, that quantity squared, plus 7. We're going to distribute that negative sign through and drop the parentheses. So that's going to be negative x squared plus 4x minus 7 all this divide by delta x. Now let's stop here for just a second and make a couple observations. First, this cancels. Then our 7s cancel. And thank God our 4x cancels too. So we've got a lot of reductions that can clean up our problem right away. So what we're left with then is going to be 2x delta x minus 4 delta x plus delta x, that quantity squared, all divided by delta x. But hey, notice in your numerator, every term has a delta x. So let's factor that delta x out. You're gonna have delta x times the quantity 2x minus 4 plus delta x, all divided by delta x. That's another reduction, because the delta x's cancel, right? So once we get that weak shit out of there, yes, I just said that, I am cool. We get 2x minus 4 plus delta x. So that's a lot of work. There's a lot to keep track of. Notice this is just one particular function though, right? We could change this to another function, let's call it g of x. And instead of having it equal to this polynomial, we could have it equal to 1 over x. And we would get something totally different. But the process would be the same sort of steps, right? And that's the point of this notation, is to say, most of the work's going to be similar. Makes sense, what I mean? So just comparing steps in work, they start by saying, hey, replace every one of your x values with x plus delta x. Then do all that algebra till you get to this part. You can't do anything else with it, not really. Now moving to part B, the same thing. From here to here, we've got a bunch of cancellations. Sweet, we love cancellations. We can factor out a delta x. When we do, we get this. Notice there is a rule though. Delta x can't be equal to 0. But that happens from the very beginning because we say delta x is in our denominator. Our denominator can't be 0. So all this rule down here at the bottom, delta x can't be equal to 0, it's an artifact from what we started with. Makes sense what I mean? It's just a rule that if these things are going to be, in fact, be equal, then this delta x can't be 0 either. But it doesn't stop it from being able to get close to 0. And that's a very important point to notice here. All we're saying is this delta x can't be 0. That's it. But we can get as close as we want to 0. And I make that point because we're going to use it in a little while. So, very quickly, the composition of functions. We oftentimes will write it with an open circle, just because this notation can get really confusing really quick. If you have like 3 or 4 functions that you're taking the composition of, that can look like a mess in no time fast. So we oftentimes will use this open circle, use that notation instead. And it's just because it'll look cleaner. That said, notice you're putting g of x inside of f of x. So at most, your domain can be the domain of g. But f of x could restrict you from not being able to have certain values too. Does that make sense what I mean? So let's say we have two functions, f of x, g of x. The composition of g with f, writing it this way means you're going to pass f inside of g, like that, right? So this thing, you can put whatever number you want inside of here, right? But this thing, you can't put 0 inside of it. So the domain of this would be negative infinity to infinity. The domain of this would be any number but 0. So the domain of this composition will be this restricted to this. Does that make sense what I mean? So let's write this out to see better. I had an eraser right there. Why don't I use my hand? X squared minus 4x plus 7. So this thing can take on whatever value we want, right? But this entire thing can't. We're restricted to a domain where x squared minus 4x plus 7 is not equal to 0. Is everybody cool with this? So this can take in any number we want, but here we're going to have to throw out two numbers because this has two roots. So the domain can be at most g, but it'll be restricted by f. Is everybody cool with this? Cool. Similarly, if we have reversed the order, if we had written f of g of x, well, that's f of g of x. So this is going to be 1 over x squared minus 4 times 1 over x plus 7. So notice the domain here is every number except for x equal to 0. Also, the compositions when they were swapped aren't equal, right? So what I mean to say is so another important observation is changing the order of our composition changes the solution as well, right? It changes the entire function. This thing is definitely not equal to to our previous thing. Everybody cool with that? Another description of how you can think of it. It's the inception of functions instead of dreams. It's a function inside a function. That was a TV rep. You really good? I am killing it up here. Man, y'all are stone cold faces today. It's brutal. Maybe Bill Murray.
It's before my time.
Really? Before my time? Okay. Cool. Now I know who wants to fail this class.
It's not me this time?
Oh, well, you're still in the failing sections
Darn
now.
it. I'll get out of there one day, maybe. I
Mm,
know.
mm.
Yeah.
So as another example of how the order of composition changes the value of your function. Let's say we have these two functions, 2x minus 3 and x squared plus 1. If we take the composition in one way, we're going to get 2x squared minus 1. Once we simplify it, taking it the other way, you're going to get 4x squared minus 12x plus 10. So they don't necessarily preserve each other. Sometimes they do, and that's really convenient, really nice. But more often than not, they don't. Now, there is a special case when the composition of functions come out to be equal to x. When this happens, we say that the functions are inverse functions of each other. One common example, quick, easy example, x squared and the square root of x. They undo each other, right? So they must be inverse functions of each other. However, something we should note, let's say x squared is equal to y. Then we would say that x is equal to plus or minus the square root of y. So this isn't a function here. But if we restrict the domain to just the positive part, it is a function. And it is the inverse function of what we started off with. So this is kind of back to that point of what you were talking about, the plus or minus, or the y squared. You can restrict the domain of a function to force it. You can restrict the domain of the inverse of a function to force that inverse to become a function. We could have just as easily said all negative values. It would still be equally true, right? Is everybody cool with this? So whenever we have the case of the composition of functions coming out to be x, we say that that composition is the composition of inverse functions. Now, a cool special trick happens, a special behavior happens when talking about the inverse of two functions. Their graphs are the mirror images of each other across the line y equal to x. Why is that? What's happening that would make this true? What do y'all think? Well, what's happening is that, let's say f of a is equal to B, right? Then this means we have the ordered pair AB, right? We're gonna graph this. This would be the ordered pair that associates with this solution of our function, right? Make sense what I mean? Well, if that's the case, we know the inverse function then of B, well, that has to send us back to X. So that's A. And that is going to associate with an ordered pair B, A. And these are the mirror images of each other across the line y equal to X. Is everybody cool with this idea? Kind of sort of? It's a little weird at first. But I point this out because it gives you a bunch of cool properties down the road as well. Think about what this would mean about the slope of a function compared to the slope of its inverse function. So we could go through and find a bunch of different inverses. And these are just a list of functions and their inverse functions. Kind of get us familiar and acquainted with the idea. I'm going to jump through these. This actually points out the point I was making about restricting the domain and the range of a function and its inverse. So typically, we would say this function has no inverse. And the reason why is because there's two different y values that have unique x values, right? So we're going to reflect that. The reflection of this graph across the line y equal to x. It's going to look like this. This is f inverse of x. This is x equal to 3. This is y equal to 2. And this is y equal to -2. So we don't have an inverse function for this. But if we were to say, let's only care about 0 and beyond, then the reflection would be just that. And now we do have an inverse function. And this is what we're doing when we say we can restrict the domain or the range of a function so that we have an inverse. Does that make sense what I mean? So typically, this thing doesn't have an inverse function. And the reason why is because to undo our function, we need a plus or minus. But we can restrict that domain to force it to happen. And what we would be doing there is saying, just choose this part, the positive part, or just choose the negative part, whichever you want. Is everybody cool with this? Yeah. It's a weird concept, I know. And I am running through this really quick for the sake of time, because we have to get into what are called limits. A limit is exactly what it sounds like. So what a limit is doing is saying we have some C value. And when we get close to it, our function's going to get close, maybe, to some L value. All right. This is going to take some explaining, I know. What we're saying with a limit is we've got this function, f of x. As x gets close to c, what happens? That's what this is answering. And the way it does it is it says, let's imagine we have this extra value, call it delta. We're going to subtract delta from c, and we're going to add delta to c. When we let delta get really small, let's let delta get close to 0. What happens to our function? If, when this delta gets really small, L plus some number and L minus some number approach the same value, then we have a limit. And in all reality, this is actually backwards because we start with L and move to C. But the intuition is that we close in on x. And when we do that, we move along our function. And somewhere in the y-axis, we see the shadow moving up and down, closing in on an L. This is if the limit exists. I should have said that. We're going to have another case in a little bit where it doesn't. This is intuitively what the limit's doing. It's saying, take a point, any point. Close it into your x value of a particular choice. In our case, C. So let's approach C. X approaching C. Does your function get close to L? If it does, then we say the limit as x approaches C of f of x is equal to L. Now, what does that mean? Well, that means looking at things like this. As x gets close to 1, can x ever be 1 in our function here?
Yeah.
Yeah, you can. We can put 1 into that. Right? Nothing changes. And as we get close to it, we kind of converge to the same value as if we were just going to put 1 in, right? So what I'm saying is, we're not looking at a function that does something like this. Our function isn't doing something like this, right? Where our function value at C is 0, but close to C, it's something totally different, right? It's not doing that. No, what we have here is something nice, smooth, and continuous. Our function here is this guy. And as we get close to 1, we get close to whatever our function is equal to at 1, right? Make sense what I mean? So we can just plug in x is equal to 1 here and get out our answer. So the limit as x approaches 1 of x squared plus 1 is just going to be 2. One way we can see this is by creating a table and letting x get close to 1. What the limit answers isn't the question, what is your function equal to at that point? That's not the thing it answers. It's answering if that point were to exist, if your function were to be continuous, what would that value be? Is that cool with everybody? So we're not answering literally what's the value of your function, because we could put a hole here. So as another example, let's take x squared plus 2x plus, well, let's just have x squared minus 1 divided by x minus 1. This thing is the function looks something like this. This here is 1, 0. No mistake, 0, 1. And this here is x equal to 1. So this would be y equal to 2. All right. Our function here doesn't have a value at 1. And why is that? Well, if we put 1 through here, we get 0 in the denominator. But what the limit would tell us in this case, so let me get this out. G at 1 does not exist. But what the limit would tell us is that the limit as x approaches 1 of g of x is equal to 2. And that's because what the limit is actually saying is, what does your function get close to when you get close to x? What is this guy, as x gets close to 1, what does this guy get close to? Well, in our case, it got close to 2. But our function at 1 didn't exist. Makes sense what I mean? Does that sort of delineation help a little bit? It is a bizarre concept, I will admit. So what we are literally saying in this first example, the limit as x gets close to 1 of x squared plus 1, is when x gets relatively close to that value 1, is our function getting close to the same value from both directions? If so, then we would say our function is equal to whatever that value was. Here we can see it gets close to 2, right? So as we approach 1 from the left, and as we approach 1 from the right, our function from the right gets close to 2, and our function from the left gets close to 2. So our limit must be 2 in this first example up here. which is not the same thing I drew on the board, obviously, right? They are related, but not quite the same. So what we're literally doing is closing in down here and finding that we close in along our depth. So as x gets closer to 1, our function gets closer to 2, hence the limit is 2. So we could look at these now graphically. Notice this first example is what I've got up here on the board. Let's look at that really quick. We've got x squared minus 1 divided by x minus 1 as the limit of x approaches 1. They're saying this is 2. But our function doesn't actually exist at that point. We're just getting close to 2. That's all we're saying. We can figure this out tabularly or graphically or algebraically, as we'll see later. In this case, we have the limit as x approaches 1 of the absolute value of x minus 1 over x minus 1. And we say the limit doesn't exist here because when we approach 1 from the left, we get close to negative 1. When we approach 1 from the right, we get close to 1. So these two terms aren't in agreement, right? We don't agree coming from both directions, so we just say we don't know what to pick. Doesn't make sense to say the limit exists here because we don't approach the same thing from two different directions. So we don't, our function doesn't approach anything at all. Not in the sense of converging in both directions, right? We can see that tabularly. Approaching from the left, we get negative 1. Approaching from the right, we get to 1. Now, this is that other point I was making about what's called a type of discontinuity at a point. The terms dropped out of my head for whatever reason. Doesn't matter though. What's happening here is we're saying, yeah, our function has a solution at 1. But as we get close to 1, our function doesn't get close to that solution. It doesn't get close to 0 here. It gets close to 1. See what I mean? So as we close in, from the left to the right, what we see is closing in on this point has us closing into 1 on the y-axis. That's what's really happening. So the limit doesn't answer the question, what is your function at the value? It answers the question, what does your function get close to as you approach that value? Again, we could have shown it tabularly. We'll see in a minute here, we can show some of these algebraically as well. So, if our function gets close to L as we approach x, as x approaches c, then we say the limit as x approaches c of our function is L, or the limit of f of x as x approaches c. You can say that in like 1,000 different ways. But the same idea applies. We want to preserve that meaning, right? Now, just some important properties to know. The limit of a constant is just going to be that constant. And that makes sense because it doesn't matter what x value you have. If y is equal to a constant, say y is equal to 1, well, that doesn't change no matter what your x value is. It's still 1, right? If you have the limit of x as x approaches c, then that's just going to come out from c. The limit of x to the nth when you see the n, and then the root. This is a special case though. N has to be even. Well, I shouldn't say n has to be even. If n is even, c is positive. That's what I mean to say. And that makes sense because we can't have an even root of a negative number. Now, how do operations work? Well, generally, we're going to preserve most of the things that we would expect to preserve. If we're going to multiply by a constant, so multiply a function by a constant, the limit is just going to come out to be the limit of our function times that constant. Does that make sense? What we're saying here is if f of x approaches L as x approaches C, we want to multiply this whole thing by some constant. Then the answer is just going to be L times that constant. That's what this first rule is telling us. The second rule is telling us you're taking the limit of two functions and adding those two functions together. Let me write this one out actually. I think these will be easier to see written out. One. M times the limit as x approaches c of m times f of x is equal to m times the limit as x approaches c of f of x. Two is saying the limit as x approaches c of f of x plus g of x. Well, this thing is going to be the limit as x approaches c of f of x plus the limit as x approaches c of g of x. The product limit as x approaches c of f of x times g of x is equal to the limit as x approaches c of f of x times the limit as x approaches c of g of x the limit as x approaches c of f of x over g of x is equal to the limit of f of x as x approaches c divided by the limit as x approaches c of g of x then we have the power rules. The limit as x approaches c of f of x raised to a power is equal to the limit as x approaches c of f of x, that whole thing raised to a power. The root rule is similar. So these are the properties that we care about, as well as the radical rule, which is really just the power rule, and that's why I'm not writing it out again. That said, I should point out, anytime we have something like this, this is really just equal to x raised to the 1 over nth power, right? So the radical rules are really just your power rules by and large. Make sense? That's why I'm not writing out 6. Okay. So that's a lot of rules. How are we going to use all of them? First, I'm going to change the color of number 1 so that you can distinguish it from number 2. All right. So the first decent example we can see is a polynomial. We're going to apply the limit to a polynomial. Well, according to rule number 2, we can break up the limit of functions added together as the limit of a function plus the limit of another function, right? So this says we can think of x squared, 2x, and 3 as their own unique functions. And because of that, we can break up our polynomial into each of the 3 terms and distribute the limit onto each term. When we do that, we're just going to apply the limit to x squared. Well, we know the limit as x approaches c of x is just c, right? And we know from the power rule that we can pull out that power, agreed? So we can apply direct substitution to this. Similarly, we can apply direct substitution of this. The limit of a constant is a constant. So this isn't the exact same problem, but it is an analogous problem to show the same sort of rules. All right, here we can apply the rule number 5 that we were just previously talking about and property number 2 here. And say this thing, this first term, is equal to the limit as x approaches 1 of x squared plus here, in the second term, we can apply this first rule and bring out this 3, right? And then finally here, the limit of a constant is just that constant. So let's keep 13. Go ahead and evaluate that one. Now, the limit as x approaches 1 of x, that's rule number 2 here, right? Excuse me. So we can just substitute 1 in. Similarly, for the second term, we get 3 times just 1. Minus 13. So now we can finish evaluating all of this. This is going to come out to be 4 minus 13, 4, negative 9. So looking at it step by step, all we're doing is applying these rules as much as we can. Again, obviously I didn't use the same polynomial they did. That is what they're trying to say here, is that you can use what's called direct substitution. Direct substitution is this rule right here, number 2, for the second property. And the reason why you can apply direct substitution is because of this 5th rule and this 1st rule. Is everybody cool with that? Now, we can have 2 functions that are equal everywhere except at a single value, x equal to c. And we can think of one quick example. That I've already shown on the board. All right, these 2 functions are equal everywhere except at x is equal to 1. So we've got the function x plus 1 is equal to f of x. And we've got the function x squared minus 1 divided by x minus 1. So what's happening here? Why is it that these 2 functions are equal everywhere except at this one spot? Anybody see it? What happens when you simplify g of x? Let's try that really quick. So g of x, x squared minus 1 over x minus 1. This thing can be rewritten as x plus 1 times x minus 1, right? All divided by x minus 1. Well, hey, we've got a cancellation up top, don't we? Get that out of there, get that out of there. So what this tells us then is that g of x is equal to x plus 1 when x is not equal to 1. Now, why is that? Well, that's because when x is equal to 1 here, our denominator is 0, right? So simplifying it, we got rid of that whole. But getting rid of that whole made it not equal to our original function, right? Getting rid of that whole, doing just this, got us to here. But these two functions aren't equal. So what we have to do is say, this is equal to that whenever x is not equal. Does that make sense? So in that way, now, when we want to evaluate this thing, all we have to do is apply the limit to x plus 1. And the reason why is because if these two functions are equal everywhere except at that one point, well, then every value has to approach the same number, right? And if this thing is continuous and this thing is not, then the limit here is going to be equal to the limit here, but here we can just directly apply x is equal to 1. So everybody cool with that? Does this kind of make some sense? Yeah, it's going to take some time to work with this. So don't feel like you have to catch it right away, because you don't. This is not immediately obvious. For example, with x cubed minus 1 divided by x minus 1. Okay, so I know I'm going to factor out x minus 1, but those factors are not immediately obvious to me. I'm going to be totally upfront with you all about that. I do know there's going to be a hole right there. Okay. Once we factor out x minus 1, we're going to get x squared plus x plus 1 times that other factor, right? And what we're saying here, when we simplify, when we divide out, is that this thing is identical to this everywhere, except at x is equal to 1. So the limits of this will be the limits of this. Because it's about what y approaches as x approaches a number, right? And if they're identical almost everywhere, then it stands to reason y is going to approach the same value almost everywhere. And if that's the case, let's not worry about this limit. Let's look at this limit. Finding the limit here will tell us the limit there. So now we've simplified it. We found an analogous function, something we can use to find the limit of that asinine beast monster problem they gave us. So now we can apply the limit directly. When we do, we find that the limit as x approaches 1 of x cubed minus 1 over x minus 1 is equivalent to the limit as x approaches 1 of x squared plus x plus 1. And that last limit we can just apply directly, just like we did a minute ago on the board. And now, lo and behold, we've got our answer 3. This is going to take some work to get used to and get comfortable. This is one of the few times when teaching this course that I really feel bad about how little time we get to spend on this, because it does take some time to get comfortable. Normally I would try to spend 2 to 3 weeks on this alone, just to be like, all right, this is what the stuff is. Let me really break it down for y'all. Unfortunately, we don't have that sort of time. So we're going to spend the next day and a half, 2 days on this. That means y'all are gonna have to spend some time going through these notes and asking questions as well. I should have week 2 homework posted tonight as well. Tonight or tomorrow night. But the trick with these limit ideas is going to be identifying trends, patterns, and methods that keep repeating. Here, factor out x plus 3, if you can. And you're going to be able to do that almost right away. You're going to factor out to the quantity x minus 2 times the quantity x plus 3 divided by x plus 3. So this is going to be like the quantity x minus 2. Factor, factor, factor. If you're not comfortable with factoring, get comfortable for the next day or so. But again, the trick with these is identifying trends and patterns. Factor, always just assume factor. Worst comes to worst, it leads you nowhere. Best comes to best, you got your answer right away. If factoring doesn't work, long division. Long division is the other big one that's going to help out with something. It'll help more so down the road. But again, identifying the patterns. Having said that, don't just memorize the algorithmic approaches to these. Understand what's happening to it. What is really actually happening, like I said, is we start off with this function with a hole up here, right? We say, well, this thing is equivalent to this other function that doesn't have this hole. It's equivalent everywhere else. So whatever this thing approaches, this other thing damn sure better approach those values. So because of that, we don't have to find the limit here. We can find it there. And that's all we're really doing, swapping out problems, saying, I don't know how to answer this because I can't plug in 1. Since I can't plug in 1, I don't know what we're getting close to. But that one I do. Because I do here, cool, awesome. That's all she wrote. That's the whole idea here, is swapping out problems for something that you would prefer. Having said that, let's see if I still have those. I don't think. I'm not on this computer anyhow. I made a GIF the other year when I was, yes, GIF, not GIF. Okay. Anyone who wants to fight me on this, let's go. So I made a GIF the other year for my calculus class that explained the limit in all 3 cases: the jump discontinuities, the plane-wise discontinuities, and just the general discontinuities. So it showed what's actually happening and gave you a better sense of what this math is saying. And I intend on posting that sometime tonight. It is 9 o'clock, so probably gonna end up being tomorrow. I'll be honest with you all. Having said all of that, because we're not gonna be able to get through anything more in the next 15 minutes, other than a problem or 2, I'm gonna let you all go right after this problem. I do want to touch on this one. All right, this problem is one where factoring alone won't help. Long division alone won't help either. What you want to do is you want to multiply by the reciprocal. And what that's going to look like is saying, you're going to get rid of this radical. You got to get rid of it in a way that actually helps me do a thing. So let's recall something we talked about last Wednesday. Let's recall this formula. The quantity A plus B times the quantity A minus B. This thing is equal to a squared minus b squared. The way we're using it here is we're saying, let's call A the square root of x plus 1. And let's call B 1. Then A plus B, the quantity, times A minus B, the quantity, is going to come out to be x plus 1 minus 1. We're going to use this to get us through this problem. We're going to use this by saying, it can't just multiply by x plus 1 square root of that quantity plus 1. No, I'm going to have to multiply by 1. But I can represent my 1 as this fraction, right? This doesn't change anything for us. Nothing actually happens here that's going to hurt math. Agreed? So because of that, multiplying by 1 and selecting 1 to be represented as the conjugate of our original numerator, we can make that new numerator nice and tidy for us. We've got a lot of reductions that are going to happen. Finally, we get down to here. And this we can evaluate directly. We've gone from letting x go to 0 here, where we couldn't evaluate that directly, to letting x go to 0 here, which we can evaluate directly. And we did that by multiplying by the conjugate of our numerator. Having said that, that is all I really had to say about this problem. I just wanted to at least show you all these. Again, I should have week 2 homework up most likely tomorrow.
So is that due next Wednesday?
Yes.
Okay.
Oh, it'll be due tomorrow. Okay. Get rid of it. Well, I have any questions?